This video tutorial is going to focus on an aspect of river hydrology involving hydrographs and flow duration curves. Specifically, we're going to learn how to create both a hydrograph and a flow duration curve and how to interpret them. All conventional hydropower plants require two key things to produce electricity, and that is A, stream flow, and the other thing is elevation. So stream flow refers to the amount of water that'll flow by a given point in the river for a given time period. And that's typically expressed as, for instance, cubic meters of water per second. Sometimes it'll be liters of water a second, or sometimes gallons per minute of water. So every minute, a gallon, so many gallons will flow by that given point in the river. The other thing that's involved is elevation or head, and that is essentially the vertical drop from the beginning of the power plant hydroelectric process to the end. And that's the vertical drop, and that'll typically be expressed as meters or feet. Both of those combine together to give electricity. The more flow and the more head, the more power is available. This video is focusing on stream flow. Hydropower developers need to determine how much electricity is available from any given site in order to determine whether the project is feasible even. Most of the rivers and streams in North America, certainly, and generally in the civilized or Western world, have been charted at one time or another by governments or other organizations. Some of them have not, and it's up to the developer to come up with their own records if there is no existing stream flow records. But in any event, you need a good set of stream flow records to determine the hydropower potential. The longer, the better. 15 years is ideal. Here's what a set of stream flow records and a hydrograph looks like. So, this is a small sampling, but the stream flow records here are sorted by date, meaning earliest to latest, or in sequential order, April 1st to the 10th. Each day has a flow associated with it, and these records are put onto this is a simple XY bar chart. So the y-axis, or the vertical axis, has the flow in cubic meters a second. The x-axis, or the horizontal axis, has the dates in sequential order, or time series, this is known as. So the 1st to the 10th, and the amount of flow for each date. While hydrographs do provide some information and they're relatively easy to understand, they are only of limited value in determining hydropower potential. For that, we have to take the information from stream flow records and develop them into something called a flow duration curve. Here's what a flow duration curve looks like. It is also an XY chart, and on the y-axis we still have flow here in cubic meters a second, but the x-axis, instead of being dates or weeks or years or months, it's something else. It's called the percentage of time. So what this is telling us is, for instance, at 80% of the time, this chart is saying that we would probably have a flow somewhere around 35 cubic meters a second. Here's how a flow duration curve is developed. So we're taking the stream flow data that we had on previous slides, and whereas it was sorted by date, the same data has been taken and been sorted by flow from lowest to highest. Carried across to this chart on the right side, that same data is here, sorted from lowest to highest, but now there's a new column. It's called percent exceedance. And what this chart means is that, for instance, at 0.25 cubic meters a second, that's available 100% of the time. Here's how these numbers percent exceedance numbers were developed? We know, because we've sorted this chart from lowest to highest, that this row of data, for instance, there's 10 data points in this chart, 1 to 10. We know that all 10 of these are at least 0.25 cubic meters a second or greater. So here's the math to develop the percent exceedance. So 10 times 10 data points in this chart are 0.25 or greater. There is a total of 10 data points, and that equals 1, or in percentage, 100%. Let's take the 7th down here. That's 1 cubic meter a second of flow, and we know from this chart that 7 of these 10 values are at least 0.1 cubic meter or greater. So here's the math. 7 divided by 10 equals 0.7, or 70%. Here's all the percent exceedance calculations from the previous slide played out row by row. Finally, we take this data and we can develop the flow duration curve. So, for instance, all these data points have now been plotted on this XY chart. So at 70%, what this chart is telling us is that at least 70% of the time we can have a flow of 1 meter a second. By comparison, 20% of the time we can expect to have a flow of 3 cubic meters a second. You can see there's those numbers, and there's those numbers. Hydropower developers will try and use some numbers anywhere between 80 to 85 to 95%. Quite a bit less flow, but it's available more of the time, so we can make more even base power. Whereas some of these higher numbers, at 4.5, for instance, cubic meters a second of flow, quite a bit of more power is developed from that flow, but it's only 10% of the time. We need something that's more even, and that's why the developers will take these numbers along the bottom. This concludes the video tutorial on flow duration curves and hydrographs.